Hi, my name is Jim McDonald. I work for TI's SVA Power Products Division, and today I'm going to be talking to you about PMBus, and specifically we're going to talk about how we use this industry standard digital interface to help you develop more intelligent power systems. We're going to start off with an overview of PMBus. We'll talk about the hardware interface, the protocol that is used, and then we're going to talk about the different classes of products and how they can benefit different use examples. And then we're going to talk a little bit about the applications that are popular, and then we'll mention what the PMBus group is working on, and then we'll show you a demonstration of a real live system using PMBus to the entire power system. So as the title indicates, I'm pulling a page out of Bob Pease's regular articles where he talked about analog circuits. And this excerpt is specifically from his very first column. And in here, he talks anecdotally about that, everyone knows linear circuits are dead. Nobody's buying or designing linear. They're being replaced by digital. So, analog is dead. Why even bother? And I think this is an important data point because he goes on to say, while digital power continues to grow in popularity, analog circuitry will continue to be required to achieve the performance levels that are demanded by our power systems engineers. And I think this is a critical theme that you'll see as I go on. So let's talk about PMBus. Well, first of all, what is it? It is a standard for communicating with power management devices using a digital serial communications bus. And the three main functions are configuration, control, and monitoring of these PMBus devices. And that means that there must be some kind of a system host, and that host can be a microcontroller, a personal computer, or it can be a piece of test equipment in a lot of cases. So how did PMBus come to exist? Well, the equipment manufacturers and the power supply manufacturers all wanted a way to communicate with the system so that they can configure it for very specific tasks or a specific application environment, so they can monitor it and make sure that the health of the power supply is consistent. And they also wanted to be able to quickly act on any kind of issues, either to optimize it for performance or to protect the equipment so that they can eliminate service returns. And in the early days, digital power supplies, they suffered from a lack of features or capabilities. So they really had limited health management. It was a non-standardized command structure, so every time you tried to add a new device, you had to rewrite the code. And it was a less than optimal communications bus structure. So one of the things that PMBus does is bring an open standard to bear on the market. And PMBus is owned and regulated by the System Management Interface Forum. It's got open membership to anyone who wants to join. It's a royalty-free protocol. Specifications are available on the website, and it works with all kinds of power management products, anything from an AC to DC or an offline supply to all kinds of DC to DC converters, whether they're isolated or non-isolated, as well as some specialized power management devices like hot swap controllers, power monitors, sequencers, and programmers. So then it's important to say what PMBus is not, because it is not all-encompassing. So it is not a standard for a DC to DC converter. We do not specify form factor, pinout, or efficiency. That's really left up to the power supply manufacturers or the alliances to define. And there are examples out there like Pola and DOSA who have taken that spec and incorporated that into a form, fit, function compatible specification. The other thing that PMBus does not specify is converter-to-converter communication. This is really a host-slave type of environment, so PMBus devices are all acting as slaves. So peer-to-peer type of communication like current sharing and analog voltage tracking are left out of the spec. That's left to the IC or the power supply manufacturers to take care of. And the main reason why is that adding these in would really limit the future innovation capability of the devices that customers are going to use. There are a total of about 43 members in the PMBus interface forum, and they are come out of three categories: either IC vendors, power IC vendors, power supply manufacturers, as well as some equipment OEMs. And we have a board of directors group that is responsible for making sure that we're making progress, that we're managing the specifications, and this comes from a number of both the IC vendors as well as the power supply manufacturers to make sure that we have a good cross-section of people that are providing those solutions to the end equipment manufacturers. From a protocol perspective, PMBus relies on an industry standard hardware interface called SMBus. It's very robust. It has monitoring with an alert-based system to reduce the amount of bandwidth that it takes, and it has error correction. It is a standards-based command set, so it has a lot of standardized commands that are handling all of the popular functions for configuration, control, monitoring, and fault management. The other benefit that it has is that it has a platform convergence capability where VR controllers for Intel and AMD CPUs already support PMBus, so there are multiple devices that are already being specified for use in computing power systems, which means that now you can make that system much more intelligent. So as a platform, it really helps to develop a more intelligent platform. And then as TI and other manufacturers continue to release PMBus products, you can be assured that they will be software compatible because they're all using an open standard. So let's talk about the hardware interface. A hardware interface is really three lines from the SMBus perspective: is clock, data, and alert. And the alert line is literally just for each of the slave devices to alert the host that something has occurred and to go and service it. This is a primary difference between I2C and SMBus, and this really saves a lot of polling, which eats up a lot of bandwidth on the bus. And then the other line here is a control or an on-off line that is typically used. Each of these devices does need a physical address so that the host knows who it's talking to, and there is the capability of doing a write protect so that you can protect against any unwanted writes. So why SMBus? I2C has been around for quite some time, and it's fairly popular in the industry. And that's just a two-wire clock and data. So there's no alert with the I2C. SMBus builds upon this capability, and so it's low cost and generally electrically compatible with I2C, but it's more robust because it has an alert feature as well as it has a timeout. So if any errant device is hanging up the bus, you can time out and you can release it, and then you can continue to communicate without having to reset the entire system. The other thing that it adds is packet error checking, so that you can check to make sure that what you wrote is actually what was received by the device. So the primary differences between I2C and SMBus from a hardware perspective there's a few key areas. One is the timeout. This is pretty critical. SMBus has it, I2C does not. The other is the clock speed. I2C specifies up to 400 kilohertz operation, and there are some fast mode devices that go up to 2 megahertz. SMBus is specified only at 100 kilohertz, but what you'll find is most of the PMBus devices today will support up to 400 kilohertz and even faster in the future. The other difference is the alert line, and then one last detail is in the thresholds. The high and low thresholds are more in line with standard TTL thresholds rather than CMOS levels, and that generally is more compatible with today's newer logic circuits. So, quick knowledge check. Can a PMBus product be used in an I2C system? And the answer is yes. So if you have an I2C system and you're looking at using a PMBus part, there are only a few things you have to be careful of. From a hardware perspective, you just have to be careful of clock cycles greater than 28 milliseconds, as it will reset the slave interface. From a word ordering perspective, you need to put the least significant byte first, which is opposite of the I2C, but that can be handled rather readily. And then on the error checking, if you don't want it, you can just ignore it. It's just another byte that you can either choose to service or choose to ignore. And we have an application note that is written and is available on the website that can help you through implementing PMBus over I2C. So let's move on to the protocol. The command language is very extensive. There are over 100 commands in PMBus. It's very comprehensive. Any command takes effect immediately, and anything you write, you can read back. It's important to note that not all devices support all commands. This would make products probably more expensive than they want to be, and certain commands just don't make sense for certain type of devices. So basically, the PMBus command set has more than 100 commands, but what you'll find is that most parts will support 10, 20, 30 relevant commands that make sense based on the application, the price point intended, and how customers want to use it. Some basic requirements are that PMBus devices, they must start up safely without any bus communication. Some must be pre-programmed, but others can be used with just pin strap settings. You can be used either with or without a power system manager or controller. So it can either be programmed through a piece of test equipment and just set it and forget it, and it's only programmed once, and then you operate without bus communication, or it can be used in a system where there is constant communication to and from the host to either of the PMBus devices. And the default settings can either be loaded from hard-coded constants in the chip, it can be pin programming, or it can be in non-volatile memory, and any of those options are available in various different devices. So how that works is a step-by-step procedure that each part goes through. Is first it checks for any hard-coded parameters that will override. That's the first place it checks. Then it goes out and looks at the pin programming as a second option. Then it will go into the non-volatile memory if there is memory and if there is data in there. And then finally, the device is ready for communication over the bus, and then that's the last method that you can use to program those operating parameters. On-off control is also very flexible. There are devices that are always on, so basically anytime input power is there, this device is turned on. And then multiple devices can be used with either a soft control pin to turn it on and off, or a hardwired pin to turn it on and off. Some devices can be programmed to accept either or only one of the above options. And the configuration commands are quite significant. This is one area where people like to use programmable devices because they can increase the range of applications that any single device can be used in. So things like setting the voltages, the margin levels, the duty cycle, the maximum duty cycle that it can achieve, the switching frequency, as well as monitoring thresholds. So for voltage, current, temperatures, if something starts getting warm or hot, you want to set a threshold so that you can go and service that equipment. Some other specialized commands that are available. Sequencing. Availability is in time-driven sequencing, where devices can support sequencing with no external support. They have a timeout or timers that can be programmed so that from the time the on-off switch is enabled, that you can wait a delay before ramping and then set also the ramp time. That's an open loop kind of sequencing. So it relies on the fact that every device before it has done what it was supposed to. If you want an event-driven sequencing algorithm that requires the prior device to have come up successfully before enabling the next device, there is some interaction with a system manager in order to close the loop. Tracking and interleaving are also features that are available in certain devices. Two other things that you can do with PMBus devices that have memory inside of them is you can embed manufacturing data, either the manufacturer of the chip, the manufacturer of the power supply, or some kind of a system manufacturing data, so that you can embed when it was built, where it was built, using what software load it was built. And then security is a big concern. So number one, error correction can be used to validate that you have successfully written what you thought you were writing into the part. And then write protect command can help prevent any kind of unwanted future writes to the part. And then some parts do provide password protection so that you can lock it down once you've verified that you have the correct programming inside the chip. One of the big uses of PMBus is to gather parametric information. So not all devices support all commands, but there's a long range of parameters that can be extracted from many of these chips. Input and output voltage, input and output current, hold-up capacitor voltage. If you have temperature sensors, it'll accommodate up to 3 of them. If you have fans, it can accommodate up to 2 different fans, as well as duty cycle and switching frequency. And these are all very popular power supply related parametric data. Fault management is another big area where it's nice to be able to tell if the part is running as it should be. So there's a long list of fault conditions both on the input, on the output, and over temperature. And each of these fault conditions has both a fault level where you want to take some kind of action, as well as a warn level where you want to observe what's happening, but you may not want to act on it yet. So this gives the customers a lot of flexibility on how they want to monitor their part. And again, all of these thresholds can be routed to the alert line so that you don't have to constantly pull the device. It'll simply give you an alert, and then you can go and find out which warning level has tripped and then service it accordingly. From a status reporting and fault management perspective, the PMBus supports 2 different alarm levels. Again, faults are major alarms. That's you really want to do something, and then the warnings are to notify that some kind of attention is needed. Fault notification options are the host can continuously poll the PMBus devices. This is required in an I2C system where there's no alert line, but the more popular method is to use the alert signal to send the host an interrupt, and then the PMBus device will go and service that fault and figure out whether it is a major, a minor, whether to keep going or whether to latch off or retry. There are many different fault response methods that are supported, and so depending on the type of fault, you can write algorithms to service them in different ways. Compliance is something that we're starting to see a lot more of. The latest PMBus specification is Rev 1.2. It is based around SMBus 2.0. Basic compliance is that any device must support the SMBus hardware interface at a minimum, and the device must support at least one PMBus command. And finally, if it supports a PMBus command, it must support it in the way that it is defined. So you can't deviate from supporting a PMBus command the way that it is written. You must use a manufacturer-specific register space if you're going to create a custom command. Now, one command does not make a successful part, so there's a growing need for additional compliance metrics. And what's happened is in the PMBus SMIF is that we are developing what we call application profile specs for specific product types. So there are more than 130 PMBus commands. It's just not cost effective to support them all in any particular device. So what we've done is create some profiles. For example, for an AC to DC converter, here are the 10 or 20 commands and the performance expectations for people that are going to build power supplies using a PMBus part. And that helps the vendors to best target how the power supply manufacturer is going to use it or the end customer is going to use it. And so as we develop these profile specs, it makes it easier for new users of PMBus to pick it up and know that they're getting just the commands they want with just the performance that they need. And then we're looking at compliance labs to see whether we can apply some kind of industry level testing just to validate that new products coming onto the market do in fact support the PMBus protocol in the way that they're supposed to. So really the next step we want to talk about is in classifying different PMBus products. And I'm going to talk about 4 different classes. Analog control with a digital interface is just with a digital interface, but the rest is primarily analog circuitry. Number 2 is an application-specific digital control circuit with specialized power processing and somewhat of a hybrid. Class 3 is really a flexible controller with specialized power processing blocks. So this is ultimately getting towards more programmable. And then class 4 is a fully programmable microcontroller or DSP-based digital control circuit. And I'll talk about each one of these and the benefits. So class 1 is analog control, digital interface. Some of the things characterize this kind of a part is it is an analog loop. So it's a continuous time response, fixed external compensation. It's very familiar if you're already used to using analog power management devices. It has a startup performance that's typically set by external components, R's and C's. It may have non-volatile memory, but it's probably not going to have a whole lot of it. So this is really optimized for a good trade-off between recognizable, consistent analog performance with some level of information to and from the chip. The benefits are that it's pretty well understood and it doesn't take a whole lot of programming. Some of the trade-offs are it may be limited to just a single topology, so it's generally focused on one particular application circuit. It may need layout changes if you want to modify the characteristics or the performance. This is similar to any analog circuit. And the performance or response may not be optimizable for different conditions without going in and changing the hardware or the R's and C's that are connected to it. So really where this is best used is where the user is comfortable with analog and they really like a deterministic nature of an analog loop. They want some digital monitoring, fault reporting, and configuration, but they don't want to do much programming, or they want to keep it to a minimal level. And in some cases, you know, they really want a few extra features, but they don't want to pay for a whole lot more than the standard analog product. So this is probably the best choice. And here's an example of a part that TI makes that fits this category, the TPS 4400. And it is a wide input range analog DC to DC controller. It drives a couple external FETs. It is a synchronous buck. And it has a lot of the same capabilities of its analog counterpart, where you program most of the operating parameters using a handful of external components. But some of the components have been minimized by making things like the switching frequency, the current limit, the soft start, UVLO, etc., programmable via PMBus. So it's a little bit of a trade-off and somewhat of a hybrid on the reliable performance of an analog loop with the programmability of a digital controller and the ability to monitor some of the parametrics throughout the chip. So this is a good example of a Class 1 product. Another example is in some of SVA's system protection and measurement ICs. And here we're looking at a whole family of hot swap controllers that use, again, an analog hot swap control loop for the inrush control and the circuit breaker control and how it operates the MOSFET that it's attached to. And that's primarily an analog circuit, but it does have a PMBus digital interface capability so that you can program the warning thresholds and you can monitor with high accuracy the current, the voltage, the power, and the temperature, and all the fault conditions out of this part. So again, a hybrid of an analog loop with extensive power, telemetry, and some programmability. So going into class 2, this is a product class that really starts to bring more digital control, a digital loop in here. So this is going to be more flexible. It's going to have programmable compensation in a lot of cases. So again, you're going to be able to use this part in a lot more applications without changing the hardware, because a lot of the compensation and a lot of the other characteristics are fully programmable. Although it may still be fixed to a certain topology, such as a synchronous buck. The benefits here are it eliminates a lot of the discrete components associated with programming, the switching frequency, the current limit, etc., and the compensation. And you can make changes to it without changing the board. So in some cases, you don't have to touch the soldering iron. It does have real-time optimization routines in some of these chips, so it can react and adjust on the fly to optimize performance. Now, some of the trade-offs are, generally speaking, this is a part that has to be programmed prior to use. So this requires one other step before you can power it on. You must make sure that it has the right program loaded. And because it's more of a digital controller, it's probably going to consume a little bit more bias current than a standard analog part. So in some portable applications, this may consume a little bit more current in standby mode. Where it's really targeted is where the user wants to be able to reuse a few components into a lot of different applications and leverage, one component into several sockets. And where they're comfortable programming the device, or there's a specific need where you must be able to program it in the manufacturing environment. So wherever you have those characteristics, this is a good choice. The last thing is where the user really understands that getting this additional programmability and flexibility comes with some price, and so there's a price flexibility trade-off that needs to be understood by these types of users. So here's an example of a Class 2 digital product, and this is the UCD 9240 series. And these are really flexible multi-channel controllers that are used with external drivers and or powertrain modules, so that you can create a dual channel, 2-phase, a single channel, 4-phase, or 4 single channel devices using exactly the same controller. So it's very, very programmable, very flexible, so it can be used in a lot of different applications. It does need programming, but we offer a complementary GUI that allows you to very easily point and click and set all the operating parameters, as well as monitor it digitally on screen and do data logging to make sure that what you've loaded is what the component received, as well as being able to monitor the operating conditions. Moving to Class 3, this is really getting even more flexible from a digital control perspective. So again, this is a digital loop control, but this is going to be extremely flexible, where it's probably going to have a microcontroller core that can be programmed into just about any topology. So a lot more flexible. In a lot of cases, what's been done is, in addition to a very flexible core, there are some very specific power hardware blocks that are used to really speed up the processing of critical power functions, such as current limit, things that you want to react very, very quickly, but you also want them to be flexible so you can program them. So the benefits are, this is really going to give you the best reuse, as it can be reprogrammed to be a boost, a buck boost, an isolated topology. In a lot of cases, this is really giving you a lot more flexibility. And the combination of some state machine hardware blocks and the flexible core means that you're going to get a good combination of speed, so performance, as well as lower power. The trade-offs are as the flexibility and the programmability goes up, so does the design complexity. So this is going to require a little bit more diligence in the design process. So the users that this type of product is really targeting are those that need a combination of really high performance, flexibility, and low standby power. They want maybe one device that they can use all over the board in multiple topologies and applications. And this is one where they should really have some software resources to do the development, because it's going to go on, this kind of a part is going to go beyond just the GUI environment, where they may have to actually write some software code. And again, there needs to be an understanding of the price, flexibility, and performance balance, because with this extra flexibility, there is going to be a little bit of a shift in the pricing. So getting a little bit more, and the customer will have to make that choice. Here's another example of that kind of a PMBus Class 3 product, and this is a UCD3K isolated digital controller. So again, it has a configurable state machine, so a lot of the A to D, the PID, as well as the PWM, and some of the current limit and other critical functions are state machine based, but still very programmable through a GUI. And then it also has an ARM microcontroller that's fully programmable. So again, it's going to give you a really good balance of programmability, but also high performance, high speed, so that you can hit transient requirements and operate at a higher switching frequency. And this just shows you kind of the what it looks like inside. Is there's a number of hardware blocks that are up here on the top that will be your standardized kind of power function blocks that need to be fast, they need to be precise, and then below is a full microcontroller based machine that is fully programmable and has a number of different interfaces, so that you can program it and or monitor it through a number of different interfaces, such as UART, PMBus, and JTAG. And this shows you just a couple applications using the UCD3138. So because of its flexibility, it can be used in a power factor correction circuit, phase shifted full bridge, a half bridge, resonant, or hard switched full bridge with synchronous rectification. So again, showing how a single chip can really be leveraged into multiple design environments. And then the fourth and final class of PMBus product is a fully programmable digital control engine. So again, this is going to be ultimate in flexibility and programmability. It's going to have a full controller core. It can be used in any topology, and this the one difference is this is going to really be more of a mixed signal microcontroller looking device that has a lot of different peripheral blocks, so that it can be used both in traditional power management applications as well as more system-oriented applications that also need some power management. So it's going to be the ultimate in programmable, very scalable, but the software support again is gone up, so it's non-trivial, and you really need to think about the required resources to support that software. We do have tools to offer, but it does require someone with software expertise in order to really get this to a final product. The other thing is, because this is a fully digital microcontroller-based system, there may be some limitations to what kind of operating frequency you can use this part in. So the ideal applications here are really where customization and flexibility is the number one must-have. If you're able to scale the core and memory for different designs, this is the kind of part for you. If you need, or if you're okay using a lower switching frequency, and AC to DC converters and motor controls tend to fit in that category where they're not switching terribly fast. Again, this is a fully digital circuit, so the bias current's going to be a little higher. So if that's not a concern, then this is a good fit. And then the last but not least is, if you're already very comfortable using a microcontroller and external peripherals, this is the kind of device that's going to allow you a little bit more flexibility in power-centric applications. And TI's C2000 microcontrollers are really a great family for this kind of an application. On the lower end, the Piccolo devices are really optimized for lower cost, more consumer-driven type of applications, whereas the Delfino and the Concerto are higher end. They're going to have floating point CPU and or multi-subsystems that are good for really more industrial and energy type of applications. And these applications here in red tend to be very popular areas where the C2000 tends to be used, and you'll see a lot of motor control and drive control. That's a real popular use for these types of devices. And then and this gives you, again, these are very flexible devices, so again you can see where you can use it in a PFC circuit, whether with a rectifier bridge or bridgeless. It can be used in full bridge, both phase shifted as well as some resonant type of topologies. And because of its flexibility, it can also be used, like the UCD9K, it can be used in multi-channel DC to DC control or multi-color LED drive type of applications. So again, you can leverage this one device into multiple applications so that you're leveraging that software capability that you've developed. So it's important that, you know, as customers start investing in PMBus, that they have all the choices at their fingertips in order to move from a traditional analog system to a fully digital power system. And one of the things that TI provides is really filling out all the components in the digital power ecosystem. So in addition to our analog, non-isolated, and isolated power circuits on the left, we also have products that have analog loop with a digital interface in this category over here, both for non-isolated power, for hot swap control, and in isolated power. But we also have complete digital loop products, both state machine based that have a really good hybrid of a digital loop, a flexible digital loop, and a lot of analog hardware processing blocks, as well as state-of-the-art mixed signal microcontroller based solutions for both isolated and non-isolated power. So regardless of what kind of part you're really looking for your PMBus application, Texas Instruments has a solution that we can help you out with. So let's talk about how people are using PMBus. Number one, easiest thing is using it in the lab. And this is pretty standard. We have GUIs that go along with all of our PMBus products and eval boards. So it's literally just as easy as installing the software on your PC, connecting the USB adapter, connecting the other side to the PMBus port of an eval module or a family of eval modules, and you can create your own power system and you can adjust it on the fly. It's fast, it's easy, and in a lot of cases you can change a lot of different operating parameters without pulling out that soldering iron. So again, reinforcing the flexibility. The other way people use PMBus is in the factory. In some cases, they want to be able to program each and every one of these devices to a certain personality or application profile before the board is really powered up. So this can be done in the ATE stage when the board is going through its bed and nails testing. The ICs can be pre-programmed before being populated onto the board, but the important thing is that it's programmed somewhere during that manufacturing process. In some cases, not all, it's really used in more of a set it and forget it type of application. And this is where, like the previous slide, the customer is going to program it before it is powered up. But in some cases, the PMBus interface is really not used at all after it's powered up. It's only used as a configuration or a loading mechanism so that you can load all the operating parameters into the chips. And at that point in time, it just operates just as any other standard analog power circuit does. It does its own thing, and no one is communicating with it. The final way that people use it, and this is probably the most popular, is where there's a little bit of both, is that there is some configuration at the front end, but there's also some interaction on a real-time basis. And the way that most people tend to use it is there is some monitoring of the critical components in the system via the PMBus to a system manager, microcontroller, or a remote host. And then there are some routines in order to optimize, adjust, and the operating parameters of the parts in order to keep them working in tip-top shape. So if things start to get warm, you can adjust voltages, you can turn on fans, you can create certain intelligent routines to keep this equipment operating as long as possible, thus avoiding field returns or service calls, which do cost companies money. And here's an example that's going on right now. Data centers are facing a tremendous challenge in that the amount of data is going up rapidly, but the electric bill cannot scale at the same time. So what they're trying to do here is to cap the power to the server blade so that they can match the power used with the task that is going on. And this is a critical function for the data center managers. So in this case, all that's really needed is an intelligent device at the edge of each node, and that's a server blade. And the LM25066 really satisfies that need by accurately measuring the current, the voltage, and the power coming into that system and managing that power consumption at the blade level. And then the system host can then allocate tasks to each of those server blades and keep them operating within that power envelope so that the electricity charges are commensurate with the amount of work that's going on. And so this is a trend that we see in the data center world. But taking that a step further is there are many other devices within the environment besides just the hot swap controller at the edge of the card. In the AC to DC power supply that is sourcing it here on the left, you could easily be using a C2000 microcontroller or a UCD3K to operate and control that power supply and connect that to the main system PMBus interface. And there are many other devices, from point-of-load controllers to VR controllers to additional system monitors that can be connected to that same bus, so that in addition to managing the power at the edge of the card, you can also manage the power touching each of the loads, so that you can now do some more intelligent algorithms on when a certain routine is running, how much power is being consumed, and then you can use that data to optimize the power consumption and ultimately to save power and the cost of electricity of running that equipment when certain conditions apply. And then in infrastructure power applications where there's maybe some higher voltages in mind, there are definitely some of those same devices that can be used throughout the system. The UCD3K or the C2000 can be used in the AC to DC offline converter. The LM5066 and 5064 can be used for the high voltage hot swap. The UCD3138 is very popular for doing a PMBus controlled isolated digital DC to DC. And then some of our digital point-of-load devices can be used for each of the different load devices. And then if there are additional peripheral cards coming into the system, something like the LM25066 can provide hot swap capability as well as power measurement to everything that is on that peripheral card. There are some devices that may not make sense to have the PMBus interface. They may not need to be programmable, things like ORing controllers, or maybe some high voltage point of load converters, and we certainly have other devices that will satisfy that. But the intent here is that you're going to have, in any given system, you're going to have some products that are traditional analog loop circuits with no interface. You'll have some circuits that have an analog control loop with a digital interface, and then you'll have some that are fully programmable and extremely flexible. And how the customer decides to really combine these devices really depends on what's needed by the system. So what's going on in the PMBus Interface Standard Committee? For 2012, we have a few major initiatives. One is to really increase the number of application profiles. The profiles really reduce the command set from that 130 commands down to something that's very, very reasonable and is just the commands you need for that application. We like to have a collaborative process between IC or power supply vendors and some of the customers that might want to use it, just to make sure we got it right. We have completed 2 of the profiles, the AC to DC and the 12-volt server hot swap. Those are available on the website. We have several others in development, including the isolated DC to DC converter, point of load converter, as well as sequencers and monitors. We're going to be doing an overall refresh of the PMBus website, including a lot more collateral on how to use these devices within traditional systems, and generally making it easier to find specs and application profiles. How you can help is, if you're interested in helping out, whether it's being one of the inputs on one of the application profiles, or whether you'd just like to be involved in helping us understand how you'd like to use it in your system, we'd really like to hear from you. And you can go onto the PMBus website that's listed here, and then there's a contact information there that you can use to submit any kind of question or volunteer. And from the application profile status, what we're doing right now is when we refresh the web page, it'll have a page that'll look something like this, where we'll show you that there are 2 application profiles that are completed, the AC to DC and the hot swap control. We're working on the point of load right now. That's an early draft and needs a little bit more work before it's completed. And then we have 2 new initiatives for isolated DC to DC, as well as point of load sequencer or manager. And once we get all these done, we will have application profiles for each and every one of the different types of power components that you might want to select for a given system. And as you'll see, we have OEM companies as well as IC companies like TI and others that are involved in creating these specifications, so that we're making sure that we're trying to make it applicable to as many customers and user types as we can. So in summary, PMBus was created to really help standardize the power supply communications. We did it based on a well-known, robust SMBus hardware interface. The protocol is really optimized for power, so it has the kind of commands that you would expect it to have. There are multiple classes of PMBus products, and each one has specific advantages and trade-offs. I've given you some examples of each of them, and there will be more coming out as we release products later this year. Picking the right device is really vital to optimizing what you want to do and how your system is going to use it. And you know, TI offers an entire PMBus power system with all of the basic classes of devices and common tool sets for a wide range of applications. So we encourage you to contact us so that we can help you design your next power system using PMBus. Okay, after the end of this presentation, we'll be showing you an end-to-end system demo using a complete PMBus power system and using the TI Digital Fusion GUI. And this demo is going to incorporate a high voltage hot swap controller with PMBus, an isolated DC to DC converter module with PMBus, as well as a multi-channel point of load converter, all with PMBus and all operating off of the same GUI. So thank you very much for your time. If you'd like to inquire about more information regarding PMBus, there's a couple emails here for general questions as well as technical questions. And if you'd like to get involved in some of the PMBus initiatives or just want to discuss how you might be able to have a little bit more influence, please feel free to contact me at the email below. Thanks very much again for your time, and we look forward to talking to you more about PMBus in the future. Hi, I'm Jim McDonald from Texas Instruments, and today I'm going to be talking to you about digital power and specifically about PMBus. What I brought with me is a PMBus system demonstration that I'm going to show you using 3 different eval boards specifically from TI. Over on the screen is a visual representation of this demo, and what we have is 3 different eval boards that are all connected together using the same PMBus interface. On the left is the LM5066 hot swap controller. In the middle is the UCD 3138 digital PWM controller, and on the right is the TPS 40422 non-isolated DC-to-DC controller. All 3 of these boards support the same industry standard PMBus interface. So now let's show you how these boards interact together. Again, on the left is the 5066 hot swap controller that takes 48 volts and protects the system against harmful inrush currents. In the middle is the UCD 3138, which takes 48 volts and converts it down to 12 volts. And on the right is the TPS 40422 DC-to-DC controller, which takes 12 volts and creates 2 different output voltages for powering digital loads. And the ribbon cable here represents effectively the PMBus interface, which is common to all 3 of these boards. So now let's go over and take a look at the graphical user interface that's used to interface to all 3 of these boards. As you can see here, up on the top, we have visual representations of the LM5066, the UCD 3138, and then on the right, the TPS 40422. Down below, what we're doing is we're monitoring and displaying the input voltage coming into the system over here through the LM5066. In the middle, we're displaying the 12-volt intermediate bus. And on the right, we're displaying the 2 output voltages, one being 3.3 volts and the other is 1.2 volts. Down below on the right, we are showing that there are 2 loads connected to those 2 output voltages. They are both static loads, one at 5.5 amps and the other at 3.3 amps. But what I can do now is I can change my load on one of those output voltages so that we can monitor the difference, and we can see that dynamically as things happen in the system, we're visually representing that change on the GUI. So then let's take a look over back on the LM5066 output, because as you can see over on the left, as we've made those changes to the load, we see that the input current coming into the system is now varying, something that we would expect. So then one other feature of this system is the ability to represent fault conditions. So what I'm going to do is I'm going to change the input voltage from 48 volts down to something that's below the 40 volt undervoltage lockout threshold, so that I can see whether the system recognizes a fault. And what you'll see in the top left is as I do that, we've gone ahead and tripped a fault condition, and we visually represented that with the undervoltage fault flag, showing that something is wrong with the system and it's alerted me that I need to change something. So the first thing I'm going to do is reset it, and then I'm going to raise the voltage back up to the nominal 48 volts. And then the last thing I'm going to do is I'm going to clear the faults, because I want it to go back into normal operating conditions. And as you can see, the fault has cleared, the red flag has gone away, The input voltage has gone back to 49 volts and everything is operating as expected again. So these are just a couple of things that you can do with these flexible eval boards. For more information on any of these products or for more information on digital power or PMBus in general, please go to ti.com/digitalpower. Thanks very much for your time.